Engineers in real-time object detection have traditionally balanced a difficult trade-off, the latency of YOLO's post-processing versus the heavy computational load of transformer-based DETR architectures. In practice, both architectures can struggle with fast-moving or blurry objects, as rigid bounding boxes fail to adapt to ambiguous target edges. This occurs because both architectures rely on bounding box regression derived from the Dirac delta distribution, which requires the model to predict fixed, precise coordinates. These fixed values do not account for localization uncertainty. The math treats every predicted edge as an absolute point, providing no information on how confident the model is in that specific location. These rigid coordinates force optimization losses like L1 or IOU to heavily penalize minor pixel shifts. This high sensitivity often results in slow convergence and limits the final accuracy the model can achieve. Calculating bounding box edges as exact discrete values imposes a ceiling on localization. To improve performance, the regression task itself needs to be redefined. Define addresses these limitations by moving away from fixed coordinate prediction. It redefines regression as the iterative refinement of fine-grained probability distributions across the decoder layers. This approach is supported by a zero-overhead self-distillation loop that optimizes the model during training without increasing inference time. This chart displays the resulting performance shift. On the COCO benchmark, the red define curve sits consistently above YOLOv10 and RT-DETR in terms of latency, parameter efficiency, and computational cost. These benchmarks suggest that significant gains in real-time detection can be achieved by redesigning the underlying regression mathematics. The first innovation is Fine-grained Distribution Refinement, or FDR. Rather than predicting single values for x, y, width, and height, FDR generates a continuous probability distribution for every possible location of a bounding box edge. The first decoder layer produces an initial reference box and a probability curve for each of the 4 edges. In the model's internal output, the red bounding box corresponds to the unweighted red distribution curves. The peaks identify initial estimates for the edges. A wide spread indicates uncertainty, while a narrow peak means high precision. This probabilistic representation provides the loss function with smooth, continuous gradients. This reduces training friction compared to the rigid penalties of the Dirac delta approach. Following the initial guess, subsequent decoder layers perform a series of refinements. Instead of recalculating the box from scratch, these deeper layers predict residual adjustments to the existing probability distributions. Non-uniform weighting functions are applied here, seen in the transition from the unweighted to the weighted bottom row. The model makes larger shifts where uncertainty is high, culminating in the refined green curves that determine the final green bounding box. FDR effectively turns bounding box generation into a multi-step mathematical refinement process, continuously improving the final localization accuracy. While deep decoder layers produce precise distributions, early layers are often noisy and less accurate during the initial stages of training. Standard knowledge distillation often requires external teacher models that increase training costs and can conflict with the bipartite matching used in DETR. To bypass this, the architecture uses Global Optimal Localization Self-Distillation, or GO-LSD. GO-LSD utilizes the model's deepest decoder layer as a teacher. As training progresses, this final layer, layer 3, generates the most accurate probability distributions, which are then fed back into the loss functions of the earlier layers. By aggregating matching indices from all layers into a global union set, GO-LSD ensures that early layers align with the refined labels of the final layer. Consequently, the early layers reach high accuracy much earlier in the training process. Because the earlier stages are more accurate, the deep layers are freed from correcting large errors and can focus on refining the final residuals. This creates a self-reinforcing loop that accelerates convergence without adding any parameters to the final inference model. The combination of FDR and GO-LSD leads to significant practical engineering benefits. The efficiency of these optimization modules allowed researchers to remove computationally heavy components that are standard in other real-time DETR architectures. Ablation data shows that GO-LSD outperforms traditional distillation methods, achieving a higher average precision than logit mimicking or vanilla knowledge distillation. GO-LSD achieves these results with minimal impact on total training time and nearly zero additional memory overhead. Even with stripped-down decoder layers, the model maintains high accuracy because its probability distributions contain more optimized localization data. Simplifying the regression task for the network facilitates a lighter model footprint while maintaining high performance. Testing on an NVIDIA T4 GPU shows dFine-L reaching 54. Fluid, iterative probability distributions converge flawlessly on targets, in scenarios where rigid bounding boxes continually struggle to maintain a perfect fit. dFine demonstrates that major improvements in real-time object detection are possible by re-evaluating the mathematical foundations of the regression task.